Good morning, children. Good morning. Today we are going to discuss the second part of this fluids, that is surface tension. If we come to the case of surface tension, basically whenever we consider the surface of a liquid, every molecule on the surface of the liquid behaves as if it is under some tension. If we consider an elastic membrane, simply a rubber cord, if we stretch the rubber cord, then a kind of tension is developed in the rubber cord. Similar to that, even in the case of a liquid surface also, a kind of tension is developed, that tension is called surface tension. And basic examples of surface tension you have to go through. Raindrops are spherical. Even if we consider small mercury drops, they are also spherical. But if we consider mercury drops which are bigger in size, if we consider mercury drops which are bigger in size, the bigger mercury drops are not perfectly spherical. Here we have to remember two things. There are two kinds of energies in the case of liquid. One energy is called potential, gravitational potential energy. Another energy is called potential energy due to the surface of the liquid. So, in the case of a small mercury drop, the potential energy is because of its surface. So, to minimize that potential energy due to the surface of the liquid, the small mercury drops take the spherical shape. Whereas, in the case of a bigger mercury drop, they will not be in a spherical shape, they will take a shape like this. Suppose if they are in the spherical shape, the center of mass of the liquid drop will be at a greater height from the surface or ground. So, thereby it attains potential energy, that is the gravitational potential energy of that mercury drop will decrease. So, to minimize that gravitational potential energy, the bigger mercury drops will be taking this particular shape. So, finally, I conclude, small mercury drops acquire spherical shape to minimize the energy called surface potential energy. Bigger mercury drops are flat like this to minimize the gravitational potential energy. These 2 points we have to remember here. Next, actually few definitions like molecular range, sphere of influence, of course they are all there, but they are not that much important for NEET exam. Because here we are focusing only on the NEET. Anyway, basic definition of surface tension you must learn, that is the force acting on the liquid surface per unit's length. Of course, Newton per meter is the unit, and dimensional formulae you have to learn, because units and dimensions is also one of the part in our syllabus. Now, suppose if there is a beaker containing any liquid, on the surface of the liquid if we put a wire, that wire in order to float, when that wire is floating on the liquid surface, then the maximum radius that it can have or the maximum diameter that it can have is given by this, and this particular letter is rho, that is the density of the liquid. So, radius, maximum radius, see this, maximum radius or diameter of the wire that can float on the surface of any liquid is root of 2t by rho r g, that is the radius, or diameter is 8t by rho r g. T is the surface tension and r is the radius, of course g is the acceleration due to gravity. So, basing on the fundamental formula that surface tension is equal to force by length, surface tension is equal to force by length, we can write F is equal to L into T, L into T or T into L. So, different cases are there to calculate the force. For example, if a wire is floating on a liquid, if a wire is floating on a liquid, for example, this is the wire. This wire is floating on the surface of the liquid. The liquid touches this wire on either side, this front side and other back side also. So, therefore, in that formula calculating for force, F is equal to TL only, but the liquid, because it is touching the wire on this side and on this side, two surfaces, the liquid is touching the wire, therefore, here you have to take 2L. So, T into TL. Like that, here we mentioned few cases. For example, if it is a circular disc or circular plate, if it is a circular disc or plate, for example, if there is a circular disc, imagine a circular disc, if it is floating on the liquid surface, then the liquid touches only on the outer perimeter or circumference, therefore, T into L can be written as 2 pi r, therefore, T into 2 pi r. Instead of a circular disc, if it is a circular loop or ring, imagine a ring floating on the liquid, because it is a ring, inside hollow, outside also no material. So, therefore, the liquid, when the ring is floating on the liquid touches the ring either outside and also inside. Therefore, there you have to write 2 into 2 pi r as the length. Like that, few cases you refer our material, different cases are given in calculating the forces. So, like this we have given different cases in calculating the force acting on that. Annular ring, for example, this is the annular ring. Annular ring means it has some internal radius, it has some outer radius, inner radius, outer radius. That means here inside it is hollow. Therefore, liquid, in this case liquid touches inside here, and also liquid touches outside also. Therefore, inner radius r1, taking that it is 2 pi r1, that is the length inside, and 2 pi r2 length outside. Finally, force is equal to T into 2 pi common into r1 plus r2. Like that, different cases, please practice the formulae depending on the shape of the object which is floating on the liquid. For example, in this example, a uniform wire of 20 centimeter length is bent into a circle. A uniform wire of length 20 centimeter is bent into a circle. So, whatever it is, length of the circle or circumference of the circle is 20 centimeter, because it is bent into a circle means like a ring. So, the liquid touches inside and outside. Therefore, you have to take L as 2L. L is 20 centimeter means 0.2 meter, of course, 2L into T. We can calculate the value as 0.028 Newton. This is one simplest example basing on the fundamental formula for surface tension. After this, factors that affect the surface tension, factors that influence the surface tension. For these factors, importantly, impurities, next factor is temperature. Basically, impurities. Even in the impurities also, there are two types of impurities. One impurity is soluble, other is insoluble or less soluble. Listen to me carefully. First one is soluble impurity. Soluble impurities increase the surface tension. Soluble impurities increase the surface tension. For example, salt water. Salt is soluble in water. Therefore, surface tension of salt water is more than ordinary water. Surface tension of salt water is more than ordinary water, because here salt is soluble impurity. Insoluble or less soluble impurities decrease the surface tension. For example, soap water. Soap water, surface tension of soap water is less than the ordinary water. Similarly, we all know that to the stagnant water, to destroy the mosquito breed, we add some oil like phenol. Why we are adding phenol or any oil to the stagnant water is, if we add any oil to the stagnant water, the surface tension of the stagnant water decreases, the mosquito breed which is floating on the surface of the water, that will sink and they get spoiled. So, anyway, concept here is insoluble or less soluble. For example, camphor. When you add camphor to the water, camphor is less soluble in water, therefore, then also surface tension decreases. So, less soluble or insoluble solvents will decrease the surface tension and soluble impurities increase the surface tension. Next, temperature. As the temperature increases, surface tension decreases. As the temperature increases, surface tension decreases. Best example for this is hot soup is tastier than cold soup. For example, if we want to take soup or sambar or rasam, I think we all prefer them in hot condition. Why? Because in the hotter condition, surface tension decreases. When surface tension decreases, spreading nature increases. Remember, lesser the surface tension, easy to spray. Lesser the surface tension, easy to spray. I think you all know that kids are playing by making bubbles with soap water. With soap water, using a straw, kids will be playing by making bubbles. With ordinary water, we cannot make a bubble that much easily. But soap water can be blown into bubbles very easily, because soap water has less surface tension, as I told earlier, soluble or insoluble or less soluble solvents will decrease the surface tension. So, the lesser the surface tension, easy to spray. So, therefore, hot soup, in the hot condition, its surface tension is less. As the temperature increases, surface tension decreases. When surface tension decreases, it spreads on the tongue and it comes in contact with the more number of taste buds, and therefore, we feel it tastier. Like that, that is the best example. Similarly, hot water bath is preferable. When you take bath with hot water, easily our body gets wet and dirt can be removed easily. So, like this, temperature effect and impurities effect you have to go through. Next very important thing is surface energy. The general formula for the surface energy is equal to W is equal to TA, where A is the surface area of the liquid film. Actually, A should be written as A2 minus A1. Suppose in the case of any liquid drop, for example, there is a beaker containing a liquid. There, in that case, there is only one surface. Therefore, W is equal to TA can be written, if the area of the surface of the liquid changes A2, A1, that difference W is equal to TA can be written. Suppose in the case of any liquid film or soap bubble, because the film has or bubble has two surfaces. Suppose if you take a bubble, soap bubble, inside air, outside air, therefore, there are two surfaces. So, the same formula W is equal to TA can be written as W is equal to T into 2 dA or 2 delta A. Why this 2 is coming? Because there are two surfaces in the case of a soap bubble. So, there are different cases. For example, what is the work done to blow a liquid drop means W is equal to 8 pi r square T, because it is a liquid drop. Drop means W is equal to TA, area of the liquid drop, area surface area is equal to 4 pi r square. So, this is 4 pi r square T only, this is not 8, this is 4. So, in the work done to form a liquid drop is only 4 pi r square T. What is 4 pi r square? Area of the surface of the liquid drop. But if it is in the case of a bubble, instead of liquid drop, if they say bubble, then it becomes W is equal to T into A is equal to 4 pi r square surface area, because the bubble has two surfaces, as I told earlier, here 2 will come. So, totally W is equal to 8 pi r square T. So, again observe the correction here, in the case of a soap bubble, W is equal to 8 pi r square T. In the case of a drop, it is only 4 pi r square T, because drop has one surface, bubble has two surfaces. Suppose if you want to increase the radius of the bubble from R1 to R2, 8 pi t into R2 square minus R1 square. R1 is the initial radius and R2 is the final radius. Like that, different cases are given. In the case of a liquid drop, surface energy go through these. So, here another case, another very important case is, if n droplets, n small droplets combine into a big drop of radius capital R. Again see here, n droplets of radius R each combine into a big drop. Here basically, first of all, we have to equate the volume of the big drop and volume of the n droplets. Volume of the big drop is 4 by 3 pi r cube, volume of the each drop, single drop is this, and n drops are there. So, volume of the big drop is equal to volume of the total n drops, and by equating them we get a relation between capital R and small r first. After that, we have to take W is equal to Ta. W is equal to T into A2 minus A1. So, A1 initially n droplets are there. So, 4 pi r square into T, n drops are there. Finally, only one drop will be there. Finally, there is only one drop, that means a single drop. Therefore, final area is 4 pi capital R square T. So, this is the surface area or work done, because the tension is also I wrote, surface tension also I wrote. So, this is the final work done and this is the initial. That difference is the work done in combining the n droplets. In this case, so many formulae are there. So, those formulae we have to remember. For example, if n droplets are combining into a single drop, what is the change in the temperature? Suppose the energy, listen to this point, energy of combining or splitting. For example, a big drop is split into n droplets. A big drop is split into n droplets. That energy of splitting, if it is used to project a body with a velocity v, let us project the surface, project the drop with certain velocity, then the velocity formula is this. Again I repeat this point, a drop is split into n droplets. The energy of splitting is used to project the drop with some velocity. What is that velocity? Similarly, a single drop is split into n droplets. What is the rise in temperature in that? This is the formula. These two formulae directly we have to remember. This is not the time to know the derivations. Basing on that, here an example is given, that is a rectangular film of liquid is extended from this area to this area. Again the formula is W is equal to T into A2 minus A1 only. But this is a film, do not forget, this is a film. So, it has two surfaces. Directly A1, A2 are given, A is equal to 4 into 2, 8 centimeter square. Final area 5 into 4, 20 centimeter square. Of course, centimeter square must be converted into meter square by multiplying with 10 power minus 4. So, after calculating you get the required answer. From that they are asking surface tension, they gave work done. They gave the work done and they are asking surface tension. You can calculate. Only the thing here you have to remember without confusion is the film has two surfaces. A film has two surfaces. If it is the case of a liquid drop, then you should not get this two. You won't get the two. Because it is a film, because it has two surfaces. Next, angle of contact. Of course, in this angle of contact, definitions and all not required. Only thing we have to remember is, for few liquids and solids, angle of contact less than 90, greater than 90, equal to 90. In some cases, angle of contact is less than 90. If the angle of contact is less than 90, those liquids will wet the surfaces. For example, water and glass. If you take water in a glass, water wets the glass. Similarly, for few liquids, angle of contact is more than 90 degrees. For example, mercury, it is around 140 degrees. So, mercury does not wet the glass. For few liquids, angle of contact is exactly 90 degrees. For example, if you take pure water in a pure silver vessel, angle of contact is exactly 90 degrees. How can you draw the shapes of those liquids means? For example, if we consider a beaker containing water, that meniscus will be like this. In the case of water in a glass beaker or any beaker, the meniscus is concave upwards. For example, if we consider mercury in a beaker, it will be the surface or meniscus will be convex. As I told earlier, if you take a silver vessel, if you pour pure water, the surface will be straight like this, straight or plane. So, here the angle of contact is less than 90 degrees, here the angle of contact is greater than 90 degrees, here the angle of contact is equal to 90 degrees. And one more point you have to remember, in the case of the liquids with less than 90 degrees angle of contact, here adhesive forces are more. In this case, adhesive forces are more. In this case, where mercury we are taking angle of contact more than 90 degrees, cohesive forces are more. Cohesive forces are more. In the case of silver here, where angle of contact equal to 90, there you can say that cohesive force, adhesive force both are equal. Similar to this, there is another term called capillarity. There is capillarity. For example, if you take a beaker, for example, if you take water, if you take a capillary tube dipped in this, then the liquid like water will rise into the capillary tube to certain height. Suppose in a similar way, if you dip a capillary tube into mercury, suppose this is the beaker containing mercury, if a capillary tube immersed, now this is the mercury column in the beaker, this is the mercury column inside the capillary tube. That means this mercury will undergo depression in the capillary tube. So, here also you remember 3 points. What are those 3 points? For liquids with angle of contact again I repeat, for liquids whose angle of contact is less than 90 degrees, those liquids will rise into the capillary tube. Example, water in a glass, water. Next, for a liquid whose angle of contact is more than 90 degrees, they undergo depression in the capillary tube. Suppose if the angle of contact is 90 degrees, they won't rise, they won't fall. The level of liquid in the beaker, level of the liquid in the capillary tube, both will be the same. Like that, for angle of contact less than 90, more than 90, equal to 90, we have to remember these cases. Okay, basing on capillarities, basing on the phenomena of capillarity, we have a set of formulae again. Fundamentally, when a capillary tube is immersed in a liquid like water, of course, as I told earlier, the liquid rises into the capillary tube up to certain height h. The fundamental equation there we have to remember is the upward force. The upward force on this liquid remember this, the upward force on this excess amount of liquid 2 pi r into T cos theta, that is equal to weight of this excess liquid. Again I repeat, when a capillary tube is immersed in a liquid like water, water rises into the capillary tube, and comparing the level in the beaker, and this height will be at some different height h. Now what is the fundamental equation? There is an upward force 2 pi r into T cos theta on the liquid which is in the capillary tube. That upward force is equated to mg. Until then the liquid rises. When this condition is satisfied, the liquid won't rise further. So this is the fundamental equation we have to remember in the case of capillarity. First fundamental equation. Basing on that, different conditions are derived. For example, there is a formula for surface tension HRDG by 2 cos theta, where theta is the angle of contact, h is the rise, here h proportional to 1 by r. Suppose if you take two capillary tubes of different radii, you can write a formula h1 by h2 is equal to r2 by r1. Basing on that, you can compare the different heights in the different capillary tubes. h proportional to 1 by d, h proportional to 1 by g. Wherever acceleration due to gravity changes, their height also changes in the capillary tube. For example, capillary tube system is placed in a lift and the lift is going up, G is replaced by G plus A. If the capillary tube system is placed in the lift and the lift is coming down, G is replaced by G minus A. Here remember again one point. If the capillary tube system, listen to me carefully, if the capillary tube system is placed, number 1, in a freely falling lift, capillary tube system is placed in a freely falling lift. Number 2, artificial satellite. Number 3, at the center of the earth. Again I repeat, at the center of the earth, artificial satellite, freely falling lift. In all these 3 cases, what is the speciality? Acceleration due to gravity is equal to 0. Because the acceleration due to gravity is 0, in all these cases, if you put a capillary tube in a liquid like water, the meniscus here will go. I mean to say that the liquid will rise. For example, this is a beaker, this is a capillary tube. The liquid will rise to the top end of the capillary tube. In all these 3 cases, the liquid will rise to the top end of the capillary tube. Liquid won't rise because the G is equal to 0. Sorry, liquid won't fall, overflow. It doesn't overflow because G is equal to 0. So the liquid will rise to the top, and moreover, the radius of curvature of the meniscus increases. In a freely falling lift, at the center of the earth, and in an artificial satellite. In these 3 cases, we can say that the liquid in the capillary tube rises till the top end of the capillary tube, and also radius of curvature of the meniscus will increase. 1 second please. Now, so this is a very important formula for the potential energy. T is equal to, I told just now, HR dG by 2 cos theta. If you want the potential energy of the liquid, potential energy is equal to general formula mgh. Already we have written the fundamental formula for the capillary rise is equal to 2 pi r into T cos theta is equal to mg. So from this equation, mg is 2 pi r into T cos theta can be substituted here. Next, from this equation, h is calculated and this h is substituted here. And by substituting all these things, and also one more point in calculating the potential energy, if this is a capillary tube immersed in the liquid, one more important point I am telling, listen. Suppose if a capillary tube is immersed in the liquid, in calculating the potential energy of that excess liquid mgh, h should be written as h by 2 because this is the lengthy column. You have to take only up to center of mass. Again I repeat this point because this is very important point. Potential energy of the liquid inside the capillary tube can be calculated like this. Suppose if there is a beaker containing a liquid, suppose if the liquid is rising to a height h, we know that potential energy is equal to mgh. In that mg, 2 pi r into t cos theta is equal to mg. So, first substitute this in this place of mg. Next, take the formula for surface tension T is equal to HRDG by 2 in this H is calculated and substituted here. But one more important point to be remembered is this liquid is a lengthy column. Therefore, in writing this H, we have to take only up to center of mass of that particular liquid, H by 2 must be substituted. That point you have to remember. So, after all we will get this equation, that is the final formula for the potential energy. Anyway, try to remember that final formula. Anyway, as I told earlier, H proportional to 1 by R, H proportional to 1 by G, all these formulae we can know. Next, if suppose, listen, this is another important point. If a capillary tube is vertically placed in the liquid, rise is H, this is H. Suppose the same capillary tube, same liquid, if it is bent like this, suppose if the tube makes an angle theta with the vertical, then remember this height will be the same. Sometimes they are asking the height in this second case, height will be the same, but sometimes they are asking length of this liquid column. Length of the liquid column in the capillary tube is calculated from this formula, L is equal to H by cos theta. And remember this, in this case height is same, only change is in the length. Next. And these are all basing on that capillary method only. So, H proportional to 1 by G, basing on that we gave an example here. And next, suppose if there is a capillary tube like this, suppose for example, if a capillary tube is placed or immersed in a liquid, listen to this point once again. If a capillary tube is immersed in a liquid, suppose it is water, it rises to some height. Now, this capillary tube is taken out of the beaker. Now, this is the capillary tube taken out of this. Then height of the liquid that remains, height of this part of the liquid that remains in the capillary tube, this is the formula. So many cases are there regarding this, and after this excess pressure. Only two formulae. Excess pressure in the case of a soap bubble, is equal to 4T by R. In the case of a liquid drop, it is 2T by R. Bubble has two surfaces, that is why it is 4T by R. In the case of a drop, it is 2T by R. And now in this case also, for example, this is the liquid in a beaker. Suppose if the bubble, if an air bubble is here at the bottom, what is the total pressure of this bubble? That is number 1 atmospheric pressure, number 2 pressure due to the height of the liquid column HDG, D is the density of the liquid, and even though it is a bubble, because it is inside the liquid, listen to this point, even though it is a bubble, because it is inside the liquid, that is having air inside, outside there is liquid. That means I am telling it is having only one surface. Again I repeat, if it is a bubble, even if it is a bubble, because it is under liquid, it has only one surface, therefore excess pressure is 2T by R. So, that is the total pressure. Suppose in the same case, if the bubble is at the top of the liquid like this, now atmospheric pressure, again it is inside the liquid only, it is inside the liquid only, therefore 2T by R, because it has only one surface. Suppose the same bubble is outside here somewhere, then it is air bubble only, therefore it has two surfaces, atmosphere plus 4T by R, atmosphere 4T by R. So, here if it is the bubble, total pressure is equal to atmosphere plus 4T by R, because the bubble is completely in air, it has two surfaces. And these are all different conditions. For example, if two bubbles combine outside like this, if two bubbles of different radii are combining outside, then this is the direction of air flow and this is the common surface. The radius of curvature of the common surface is equal to R1 R2 by R2 minus R1. That is one formula. Again, another thing is, if two so bubbles are combining into a single, this is the radius of the common bubble. If they are combining into a single, see, try to observe the difference between these two. Here in the second case, the bubbles are combining into single, but in this case the bubbles are combining outside only, they are not merging one another, they are not merging one another. In this case bubbles are combining outside, in this case bubbles are combining into a single. Here drops are combining, instead of bubbles drops are combining. What is the radius of the combined drop? And another thing is, if we consider two plates, two glass plates, in between the two glass plates, if you put a drop of water, suppose take one plate, put a drop of water, put another plate. Now you can observe easily in your daily life also, you cannot separate them. You require more force to separate them. So, what is the force required to separate the plates? This formula is very important. Where in this formula, D is the thickness of this layer, D is the thickness of the layer or separation between the plates. That formula is very important. Next, this is a simple formal problem basing on that force required to separate the plates only. That is very important, and please work out one or two models basing on that. And this is the formula, this is the problem basing on two bubbles are combining outside. What is the radius of curvature of this common surface R1 R2 by R2 minus R1? In this R1 value, R2 value are given. What is the radius of curvature of the common surface that was asked? So, like this, these are the few important points in the case of second part of fluid dynamics or fluids. So, please go through this thoroughly. You just base on our material synopsis, material problems, especially exercise 2. Again I am repeating, do not forget to do all the problems in the exercise 2. 100% you will get good marks. Thank you very much. Thank you all for today.